Occlusion project. I first wanted to kind of go over the experimental setup, but this I had shown in my presentations before, the experimental setup diagram, to give more of a picture of what that actually looks like. I'll show some pictures of the actual experimental setup. So on the right, this is just the equipment that's used. This function generator right here is the one driving the transducer, the 3.3 megahertz. Feeds into this 50 dB amplifier here that goes to this impedance matcher, which goes to the focus transducer. The unfocused transducer that acts as the microphone comes back up to the preamplifier here, and then finally to the oscilloscope. And then this brown function generator is just the one that does all the timing, half second on, half second off cycles, and is controlled by this, and tells the oscilloscope when to start a capture. This device right here is a pulse echo. I use that for focusing the transducer on the vessel. It sends out a pulse and then immediately turns into a listening mode. So as we look at the oscilloscope, actually on the oscilloscope you can kind of see here, this would be a pulse echo. This initial bang here is the pulse and then turns into a listening. And then right here behind the cord you can kind of see where there's a peak starting. That'd be about the focus of the transducer, so we want to move the transducer where that peak maximizes. This would be in the vessel, or the transducer in the vessel itself. This here is the focus transducer. It's in a bag filled with degassed water. We have to have some sort of acoustic coupling between the transducer and the vessel. However, the vessel has to be in saline. That's why this isn't all done underwater. This box here is full of saline and contains the vessel, and then the focus transducer here behind it you can't see would be the unfocused transducer acting as a microphone, and that's just in the tank of water on the outside of the box. So my design review presentation, I mentioned the fix I'd implemented for the flow rate, and that was to take out some of the jitter in the signal, so it was more of a constant flow rate. So we implemented that fix. This is the ROC curve from that set of experiments. There were 14 runs. 8 of them ruptured, 3 of them did not rupture. 3 of them we did not use because they rupture almost immediately and we get no useful data. So you can see the ROC curve is very well here, really close to what we want to see, which is step straight up and straight across. We want to maximize the area. This table here is the area under the curve. We were hoping for at least 0.75, and you can see in the low frequency, mid frequency, and then the RMS mid, RMS low, we got above 0.8, which is far better than we hoped. So that's good news, and we'll be using these results to find the threshold, RMS thresholds for controlling the transducer. The circuit itself, I'd shown this prior. The current stage of the circuit, DSP controller, main controller, impedance matching circuit for the 50 ohm coax, and voltage adjuster, take plus minus 10 volts down to 0 to 5 volts. And then I put this on a perf board. This is what I'm getting here. Quickly, because I am starting to run out of time. I have the circuit mostly working. The circuit's running now. I'm having it receive just random bits of data, and then just sending it to the computer, and the computer's plotting it in real time now. This is the working version of the script. If I go and stop this, I can show you the GUI I have set up. It's pretty simple. One set of axes, a few buttons, start the experiment, stop, pause, manual increase and decrease the voltage, if whoever's running the experiment decides it needs to be done, as opposed to the circuit deciding that. It's not completely stable yet. We'll see if I can get it to work. Let's put some random number in. That's thinking. There we go. So that's one of the things I haven't figured out quite yet. As opposed to plotting on the axes in the GUI, it'll plot on a separate window. I'm trying to figure that out, but I'm having another issue with the circuit at the moment that I think is a little bit more important. But you can see it's this is just some debugging output. It tells when it's been turned on and off and what data it's actually receiving. You can't see the scope now, but to control the half second on, half second off, it's done by the circuit itself. I have a picture of this will be done. This square wave here is when it's high, it's turned on. When it's low, it's turned off. This is just a debugging thing. I was having an issue with the SPI interrupt not being triggered every now and again, and this is what this waveform is for, just to make sure that the SPI is actually getting triggered. That's about all I did for this quarter. I'm very nearly done. It's solving some issues right here in this function for the SPI interrupt. It's not copying from the UART buffer to the SPI buffer quite correctly, but hoping I can get that figured out by the end of this week, and then to get that figured out and get the GUI to work correctly, I will be basically done. Just need to do testing then.